Deep beneath the ground in Ohio sits a machine that holds up America's skies. The Mesta 50 press, a 36,000-ton monster that plunges 10 stories underground. It squeezes metal with 50,000 tons of force. That's the weight of 10 Eiffel Towers at once. Without this machine, the United States would have no F-35 fighter jet, no Boeing 787, and when a crack appeared on the press in 2009, the entire American aviation industry held its breath. Today we'll see how white-hot titanium transforms into fighter jet wings under the blow of a steel fist from the Cold War era, and why this machine, and no other, remains irreplaceable to American defense. If you stood outside the Alcoa plant in Cleveland, Ohio, you wouldn't see anything special. Just an ordinary industrial building, gray brick walls, pipes, trucks. But head underground and you enter a world where real power is born. The Mesta 50 doesn't sit on the ground, it's embedded into it. 100 feet down, 10 stories of concrete and steel. Why so deep? Because when 50,000 tons of force slams into metal, the earth shakes for half a mile in every direction. Without this colossal foundation, the press would punch through the ground like a knife through butter. This machine was built in 1955 at the height of the Cold War, and it's still running, almost 70 years. In that time, generations of aircraft have come and gone, materials have evolved, control systems have advanced, but the press remains, because nobody has built anything more powerful. If you're into stories like this about machines that change the world, subscribe to the channel right now and hit the bell so you don't miss the next one. America and the Soviet Union weren't just racing in space, they were racing for the sky. Whoever builds the best aircraft dominates the air. And the best aircraft need parts that can't be made with conventional methods. Picture a turbine blade from an F-35 fighter jet engine. This component is only about a foot long, but it spins at 10,000 revolutions per minute at temperatures exceeding 2,500 degrees Fahrenheit. No welded seam could handle that. It would fail in seconds. The blade has to be solid, forged from a single piece of titanium or nickel superalloy. That's exactly what the 50,000-ton press is for. It doesn't cut or weld, it crushes. Takes a red-hot chunk of titanium and transforms it into the precise shape of a wing or blade in a single strike. Press forging doesn't just shape metal, it changes the metal's very structure. The crystalline grain of titanium gets refined and aligned along the part's contours, making it several times stronger than if you cast or machined the same part from stock. The process starts with prep. A titanium ingot heats up in a specialized furnace to 1760 degrees Fahrenheit. At that temperature, titanium becomes soft as clay, but keeps its incredible strength. The metal glows bright red, almost white. You can't look at it without special glasses. When the temperature hits the sweet spot, a robotic arm pulls out the glowing ingot and moves it to the press in seconds. Time is everything. If the titanium cools even 90 degrees, it becomes too hard and the press can't deform it. The operator literally has no room for delay. Every move from furnace to press is drilled to perfection. Decades of practice, hundreds of thousands of parts. They lay the ingot into the lower die, a massive steel form that mirrors the shape of the finished part. The dies themselves are made from special tool steel and cost hundreds of thousands of euros each. From above, the upper die drops, 330,000 pounds. And then the strike hits. 50,000 tons of force slams down onto white-hot titanium. To put that in perspective, imagine stacking 150 passenger jets on your desk. all at once. Hydraulic cylinders 8 feet in diameter generate pressure of 50,000 psi. That's 3,500 times atmospheric pressure. Under this monstrous force, titanium behaves strangely. It doesn't break. It doesn't crack. It flows. Metal atoms shift, sliding past one another, filling every microscopic corner of the die. In 3 seconds, a shapeless ingot transforms into a perfect replica of a wing spar or turbine blade. The entire factory shudders from the impact. Workers feel the vibration hundreds of feet away, like a minor earthquake. Operators at the press wear specialized ear protection. The sound of the strike reaches 130 decibels, louder than a jet taking off. The strike itself lasts no more than 3 seconds. But in those 3 seconds, something happens that would take hours of conventional machining, and the result is stronger. But the most amazing thing? The precision. Despite the savage force, the press controls the shape to within half a millimeter. Laser sensors track every movement of the die. Hydraulics adjust pressure thousands of times per second. If something goes wrong, a part worth 300,000 euros turns into scrap metal. Mesta 50 produces parts for all major American aircraft: F-35 and F-22 fighters, Boeing 787, Apache helicopter engines. They all carry parts born under the blow of this press. Every month, more than 2,000 tons of titanium and nickel superalloys pass through it. The plant employs hundreds of specialists: metallurgists, press operators, quality control engineers. Each finished part undergoes rigorous inspection: ultrasonic scanning, X-ray, geometry measurement, accurate to hundredths of a millimeter. Documentation for each part is stored for decades. If a plane crashes, investigators can reconstruct the entire manufacturing history of every component. Only after passing all inspections does a part receive clearance for installation on an aircraft. And then disaster struck. In 2009, during a routine press operation, engineers heard an unusual sound: metal cracking. The press was immediately shut down. Inspection revealed something terrifying. A crack nearly 4 feet long had appeared in the main support beam. For the U.S. aviation industry, this was a real shock. Mesta 50, the only press of this power in the country, without it, F-35 production stopped. Boeing couldn't manufacture parts for the Dreamliner. Military contracts were frozen. Every day of downtime cost millions of dollars. The problem was that a 2,000-ton beam can't just be removed and replaced. It's installed in the structure at a depth of 100 feet, surrounded by dozens of other systems. And building a new press of equal power, that's years of work and billions of dollars. The country had neither. Engineers would have to repair it right there on site, 100 feet down, in cramped conditions with no way to extract the structure. A desperate repair effort began. A specialized team of welders worked around the clock for 4 months. They used cutting-edge technology, electroslag welding in an inert atmosphere. The crack was welded layer by layer, each about 1/8 of an inch thick. After each layer, the metal underwent heat treatment to relieve internal stresses. In total, 760 weld layers were laid down. Meanwhile, a backup beam was being fabricated, just in case the repair failed. It was made at another facility and delivered using America's largest crane, capable of lifting 4,000 tons. In December 2009, Site 50 was operational again. 200 engineers watched the first strike after repair. Everyone held their breath. The press struck. The facility shuddered. The titanium deformed precisely to the die shape, and the crack didn't reappear. 4 months of work, 760 weld layers, thousands of hours of heat treatment. It all held. The American sky was saved. Today, the 50 is still running. It's almost 70 years old now, an incredible age for industrial equipment. Modern presses are more efficient and automated, but none reach this kind of force. 50,000 tons remains an unbeaten record for the entire country. The 50 is more than just a machine. It's a symbol of industrial might and engineering determination. Every plane you see in the sky, every military fighter, every wide-body airliner, its structure contains parts born right here, beneath the Ohio ground, under the strike of this steel fist. Over the decades, an entire ecosystem has formed around the press. Thousands of engineers, metallurgists, operators who pass down from generation to generation the knowledge of how to work with this monster. It's proof that sometimes the best solutions aren't the newest ones, but those proven by decades of reliable work under incredible pressure. Literally.
Every year, shipyards launch massive icebreakers and cruise liners, vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts. That's more than 30,000 horsepower. And dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of two fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers had been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution: move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work, it worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer. And after that, the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year. Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship, and the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom, along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel, at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000-pound capacity. giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2,200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles. Up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage, precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness, 12 inches, bend radius, 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany. And SN total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds. Because every press strike, every hour in the furnace, and every pass of the ultrasonic probe were done with zero margin for error.